Hi, welcome to lesson 2.3, equation of a circle. I'm going to demonstrate and draw a little diagram here to show the development of the equation of a circle before we get started. And so if we have the coordinate grid here, the Cartesian plane, and we have a point which I will plot around here, and that point has the coordinates x, y, I can then see, okay, well, there's going to be some sort of distance from there to the origin, and I'll just put a little dotted line here. So if I've got that distance of a circle, or of a point from the origin, I could then, now that's sort of tethered to the origin, I can spin that around the origin and I can form a circle if I just shake it around a little bit. Okay, and so we have a circle there, and so what I'm going to do is, with that, I'm going to now drop a perpendicular from the point down to the x-axis and try to make sure it's perpendicular. So there is a perpendicular there. Think about what kind of triangle that has now formed. And from there, if we know that this point has coordinates x, y, what would this distance here be? What would we call that distance along the x-axis there? Well, I would say that it would be distance x, and in similar fashion, what would we call this distance right here? How about y? Here we go. So we've dealt with right triangles recently. We dealt with them when we were developing the formula for the distance between 2 points. What formula did we start with in order to develop that formula for the distance between 2 points? Yeah, so that was Pythagorean theorem. So if we say this is the radius r, and Pythagorean theorem then states that remember, it comes from drawing squares off each of these legs and a square off the hypotenuse, then the area of this square plus the area of this square, this two sums of those areas add up to be the area of the square off the hypotenuse. So then when we found those squares, the areas, and we took the square root of those, we could find the side length of each of these legs, and henceforth the side length of the hypotenuse. So remember, when we simplified that, we've used different letters in the past to show the Pythagorean theorem, but in this particular case we use x squared plus y squared equals r squared. So that shows us Pythagorean theorem, which gives us the distance here from the origin to the point, and that point is on the circumference of the circle. Now whether that point is here, or let's say we put the point here, that point is still going to be distance r from the origin, and it'll still have a height y and some horizontal distance x from the origin. If we were to swing this point down around here a little bit more, we could see that again, that r, the radius, is a certain distance y from the origin and a certain distance x from the origin. So no matter where we go, wherever we draw this, we can spin this point around the equidistant around the origin to form a circle, we see that we're still forming right triangles, and that distance from the origin to the point, and henceforth from the origin to the circumference of the circle, is still made up of the formula for the Pythagorean theorem, x squared plus y squared equals r squared. So therefore, if we were to draw enough points and enough triangles, now in order to keep this less messy, I'm not going to draw all the triangles, but we could draw points all the way around, and even more tightly compacted than the ones I'm drawing right now. We could draw points all the way around and form triangles for every single point all the way around the circle. Each of them will have this formula to find that radius, and if we draw enough of them, we will in fact form a circle. So that being said,